So for Chapter 8, we have some additional topics in trig to talk about, and Section 8.1, we're going to talk about right triangle trig applications. So the problems we're going to be dealing with are scenarios or word problems or context problems where we will be using right triangles and the trig functions that we've talked about up to this point to find an unknown quantity. That could be a height, an angle, a distance, but they'll all be in the context of a right triangle. So we'll be able to use what we know about triangles to try and find something we are asked for using the given information that we have. So in this first problem here, we have a flagpole that casts a 15-foot shadow when the sun is at an angle of 54 degrees with the ground. So in these types of problems, the strategy is really always going to be draw a picture. So drawing a picture will kind of give you an idea of what you're dealing with. So drew a little sun up here, flagpole, and what you should come up with once you have a drawing is a right triangle. So we have 54-degree angle from the ground. So if I were to extend the line of the triangle going up towards the sun, obviously that's what creates that 54-degree angle. And then the height of that triangle is the flagpole. It's obviously not a very fancy drawing, but it just gets the idea of what we're going to be talking about. If you just want to draw a right triangle, as long as you know what parts are what, that's fine too. You don't have to, draw a sun and a flag and all that stuff, but I will. So we're asked for the height here. So if you take a look at labeling some parts of this triangle. So what we know is the distance from the flag on the bottom of the triangle, which in this case is the shadow, is 15 feet. And then the height of the triangle, which is the flagpole, is what we're being asked for. So I'm going to label that H. So if we think about what we know about triangles, going all the way back to geometry, the first thing we really talk about in triangles is SOHCAHTOA. So if we think about what this stands for and put it in context of our triangle, we have an angle, and we're being asked for the side that's opposite the angle of the triangle, and we know the side that is adjacent. So if we think about the trig function that relates the opposite side and the adjacent side, that would be tangent. So I can set up an equation and solve for h. What I mean by that is, if I take tangent of 54 degrees in this triangle, that would be equal to h over 15, or the opposite side over the adjacent side. Now if I can solve that equation for h, then I'll have the height of the triangle, or the height of the flagpole, in this situation here. So to solve for h, I would multiply both sides by 15. So I'd have 15 tangent of 54 degrees equals h. And now, for these types of problems, that is an exact answer, but that really doesn't help us understand how tall the flagpole is. So we're going to use a calculator to find this value. One thing you want to be sure of is when I type this in my calculator, I want to make sure that my calculator is in degree mode, because I'm taking the tangent of 54 degrees. You would do that in the mode button, so you hit mode, make sure that your calculator is in degrees. But then I would literally type 15 tangent of 54, enter, and I would get a height or a value of 20.646 feet. And I'm going to round everything here to 3 decimal places. And we're going to start transitioning to really focusing on 3 decimal places for a lot of our decimal answers. So the height of this flagpole that has a shadow of 15 feet with the sun being an angle of 54 degrees is 20.646. So take a look at example 2. We have a ladder leaning against the side of a house. So the distance on the ground between the base of the ladder and the house is 7 feet. The height of the ladder is 15 feet, and we're asked for an angle. The question is, what is the angle at which the ladder is leaning? So I'm going to construct a picture here. So I'm going to draw a little house. Here's a little door. Then I'm going to draw a ladder that's leaning against the house. Again, it's a really simple, really crude drawing, but it's really that triangle from the ladder to the building to the ground is where we're going to be working and finding our information here. So I'm going to go ahead and label some pieces that I was given. So distance on the ground between the base of the ladder and the house is 7 feet. So I'm going to draw that there. It's a right triangle. And then the height of the ladder is 15 feet. And what that means is not the height the ladder is against the wall. That's actually the secondary question we're asked. If you see that, it says, at what height does it reach the house? Talking about the ladder. It's actually the length of the ladder, or the hypotenuse of the triangle, is 15 feet. So what we're asked for first is, what is the angle at which the ladder is leaning? And then the second question is, what height does the ladder reach? The first thing that would be easiest to find out would actually be the height the ladder is against the wall. We have a right triangle, we know two sides. So if I use the Pythagorean theorem, I might be able to find that side length before I really get into that angle. So I'm actually going to do that first. So I just drew an arrow saying what height does it reach the house. That's going to be the third side of the triangle I don't know. And then I put a little theta in the bottom of the triangle because that's the angle that I'm going to want to find eventually. So in terms of finding that side, set up the Pythagorean theorem. So 7 squared plus h squared is 15 squared. 7 squared is 49. 15 squared is 225. Solve for h. I would subtract 49 from both sides, so h squared is 176. 176 is not a perfect square, so if I take the square root, h is approximately 13.266 feet. So that's the height the ladder is against the wall when the ladder is 15 feet and the base is 7 feet away. The secondary question, or the other question that I was asked, is what is the angle at which the ladder is leaning? So if I think about the sides of the triangle I know and the angle that I'm trying to find, now that I know all three sides, you could use sine, cosine, or tangent, but I'm going to always try and use the given information to find that angle. The reason why I wouldn't want to use 13.266 is maybe I typed it in my calculator wrong, maybe I had a wrong value for the height, and then if I use that value in my calculation, then I could potentially get both answers incorrect or be off by a little bit rather than just using the information given. So what I'm going to use is cosine, because the adjacent side is 7 and the hypotenuse is 15. So I'm going to set up the equation cosine of theta is 7 over 15. So now, here we're looking for the angle, and if you remember back to chapter 7, another way I could rewrite that is really cosine inverse of 7 over 15 equals theta. Writing it as an inverse is helpful, one, because the value I get is the angle, but also I have a cosine inverse button on my calculator, second cosine, and as long as I can make sure my calculator is in the correct mode, I can type that in my calculator and get the angle that I'm looking for. So what I would type in my calculator is exactly that, cosine inverse, which is second cosine, of 7 over 15, and if my calculator is in degrees, I hit enter, it'll give me an angle in degrees, which is what I'm going to report here. So the angle that I get is 62.182 degrees. So that is the angle for which the ladder leaning against the wall, 13 feet off the ground, 13.266 feet off the ground, that is formed. So at times you'll have to use your inverse cosine or inverse tangent, inverse sine, inverse trig functions if you're looking for an angle, or you'll have to use the correct trig function to find a side length. It just depends on what the context is. So example 3, we're given some information about an isosceles triangle. So I'm going to construct the triangle here. So I have an isosceles triangle. We're told the base angles are 75 degrees and the legs are 13 centimeters. And the question is, what is the height of the triangle? So one thing we might remember about triangles or isosceles triangles is obviously if the two base angles are the same, their sides opposite are the same. But notice this is not a right triangle. But if I am asked for the height of the triangle, if I draw a altitude from the top of the triangle to the base, it's actually a right triangle. So now I have, or it's actually a 90-degree angle which forms two congruent right triangles. So here's my setup here, and we're asked for the height of the triangle, which would be one side of one of the right triangles I have in this picture. So at this point we have to decide what trig function we want to use to relate the sides and the angle of the right triangle that I'm looking at. So if I have a 75-degree angle, h would be the side opposite and 13 would be actually the hypotenuse. So the trig function that I would use would be sine. So sine of 75 degrees would be equal to h over 13. And that would be, again, the opposite side over the hypotenuse. And then I want to solve for h. If I solve for h, then I'll have my height of my triangle. So multiply both sides by 13. So I have 13 sine of 75 equals h. And then that is an exact answer, but if I want a decimal answer, I would just type that in my calculator, 13 sine of 75, and I would get 12.557 centimeters. So in this case, we actually had to construct an altitude which formed a right triangle and then use the sine, cosine, tangent, trig functions, decide which one is appropriate, and find the missing piece of information. So example 4, we introduce possibly a new term, angle of elevation. What that really means is from a point on the ground or a point looking upward towards an object forms an angle. So from wherever you're looking up to the top of something, up above where you are, it forms an angle of elevation. In this case, we're looking from the ground, point on the ground to the top of a pyramid, forms an angle of elevation. So I'm going to try and construct a picture here. So I'm going to draw a pyramid, kind of 3D. You don't have to be, again, you really don't even need the pyramid that much, because the rest of the picture that I'm going to construct will form right triangles, and you'll kind of see how I'm going to approach this one. So here's what we have. A point on the ground to the top of the pyramid is 35 degrees, so that forms an angle of elevation. So from the top of the pyramid to a point on the ground, and then I'm going to draw kind of a height there. So from the top of the pyramid down to the bottom, and you can see that in blue there, I have my right triangle. Like I said, the pyramid is nice to have there, but it's really not going to come into play when we are trying to find what we're finding. But again, that first sentence right there is how I constructed that blue triangle. 35 degrees from the ground to the top, and then drew a altitude from the top of the pyramid to the base of the pyramid, which forms a height. And there's that first sentence. Second sentence says the angle of elevation from a point 135 feet farther back is 21 degrees. So we're looking, again, still at the top of the pyramid, but I'm 135 feet further away from the pyramid. So I would draw a point on the ground. That's 135 feet further away from the pyramid. And then construct a line from that point to the top of the pyramid. And that forms an angle of 21 degrees. And hopefully what you see at this point is I really have two right triangles. The red pieces that I drew there touch the top of the pyramid, have the same height, and then the base touches the other base of the blue triangle. So I have really two triangles, and what I'm going to refer to them as the big triangle, which is the red one. If I were to finish the red triangle, come down on the height, or the small triangle, which is the inner blue in the first triangle that I drew there. And you'll see I'm going to need both of them to find the height. So the first thing I'm going to do is kind of label a little bit more information. So the distance from the first point on the ground to the height of my right triangle, I'm going to call x. You could call it anything. I'm just going to call it x, which means the total length of the bigger triangle, the red triangle, would be x plus 135. Because if the distance from the original point to the height of the triangle is x, and my secondary point that I drew in red was 135 feet further, that makes that total side length x plus 135. Now what I'm going to need to do is, like I said, kind of relate two things, of two triangles to each other and try and solve for the height. So the first thing I'm going to do is set up a trig ratio for the big triangle. So tangent of 21 degrees equals x plus 135. And again, that's, or excuse me, h over x plus 135. So that would be the ratio of the opposite side over the adjacent side in my big triangle. And then for my small triangle, I would set up another trig ratio. So tangent of 35 degrees equals h over x, the opposite side over the adjacent side. And now the reason you need both is I'm going to use the information from the small triangle so that I can substitute in my trig ratio in the big triangle so that I'm only dealing with one variable. Okay, what I mean by that is if you look in the big triangle setup, tangent of 21 degrees equals h over x plus 135. I have an h and an x, which would make solving for h kind of difficult. But if I can use the ratio from the small triangle, tangent of 35 equals h over x, solve for h, being x times tangent of 35, if I took that and put it into the other equation for h, I'll have one variable x, and I would solve for x. So that's what I'm going to do. So I'm going to replace the h for x tangent of 35 degrees. So I have that there. Tangent of 21 degrees equals x tangent of 35, and I got that from my small triangle, over x plus 135. Now if I can solve for x, that would give me the length of the side of the small triangle, but then it would allow me to find h. I would just replace x in x tangent of 35, and I'd have h there. So I'm going to solve for this equation for x. So I'm going to multiply both sides by x plus 135. So if I distribute on the left side, I get x tangent of 21 plus 135 tangent of 21 equals x tangent of 35. So I just distribute it on the left, and then multiplying both sides by x plus 135 cancels or reduces on the right side. So now I have two terms on the left, one term on the right, and what you should notice is one of the terms on the left has an x in it, and one of the terms on the right has an x in it. So I'm going to get those both on the same side. So I'm going to subtract x tangent of 21 from both sides. So I'd get 135 tangent of 21 equals x tangent of 35 minus x tangent of 21. And then, if I want to solve for x, what I'm going to do is do something so that I can get x by itself, which, if you look at both terms on the right, they both share an x. So I'm going to factor out an x from both terms. And by doing that, I have x times the quantity, tangent of 35 minus tangent of 21. What I can do now is divide both sides by that binomial, tangent of 35 minus tangent of 21, and then I have something that I can put into my calculator and get a value for x. So one thing to be sure of when you type this in your calculator, the top of my fraction is at 135 tangent of 21. That is being divided by the entire binomial in the bottom. So what I'm going to do is put the top in parentheses, and then divide, and then type tangent of 35 minus tangent of 21 in its own set of parentheses, and that'll be sure that I'm following the correct order of operations. So what you should get is 163.814 feet. So that is the length of x, but that's not what I'm asked for. I have to take that number and put it in for x to find h. So h is going to be 163.814 times tangent of 35, which would be 114.704. One thing you want to be sure of is I didn't use 163.814 in my calculation. I used the full decimal that was in my calculator. When you hit enter in your calculator, when the number that's saved, you can operate with that number without rounding. So what I did there is, once I had my value for x, I left it in my calculator, unrounded, and then just multiplied it by tangent of 35 to make sure that I don't use a rounded answer in my calculation, because you could potentially get your final answer that's off by a few decimal places. So using the unrounded value for x times tangent of 35, I get 114.704 something something, rounded to 3 decimal places. So the height of the pyramid is 114.704 feet. And the last example we're going to talk about for the day one notes is going to be still a right triangle application, but we're going to be talking about grade. I don't know if you've ever been driving on a road somewhere. Illinois is kind of flat, but if you drive in some of our bordering states, you'll maybe see a sign on the side of the road that talks about the grade of a road. And what that really means is it gives a number for how steep the road is. So grade is really a ratio. So if you take 100 feet of road and the road rises or falls by a certain number of feet vertically, if you divide those two numbers, you get grade. What I mean by that is if you take, kind of draw like a quick little triangle here. So if I have 100 feet of road and that road rises or falls by 8 feet, like in this situation, the grade would be the ratio of that, 8 over 100, which is 8%. So obviously the steeper the road, the more vertical change for a 100-foot horizontal change gives you a higher or lower grade. So we're going to use that idea of grade to set up a triangle to answer the question here. So it says, suppose a road climbs at an angle of 6 degrees, so angle, not grade, so an angle of 6 degrees to the horizontal. What is its grade? So what that means is, let's say I draw a triangle here. So we have 6 degrees as an angle and 100 feet. The reason I know I can put 100 feet on the bottom there of the triangle is grade has a constant of 100-foot horizontal distance. And what I need to find is the height there, which would tell me what I need to calculate the grade. So drawing a right triangle here, I have a 6-degree rise, but I don't know the height, the actual vertical change, so that I can find its grade. So if I think about that, I'm just going to call that h. If I can find that height, then I can divide that height by 100, and that'll tell me the grade. So what I have here is an angle of 6 degrees, and I have the opposite side and the adjacent side. So again, the grade is going to be h over 100 feet. I just need to find h in this situation using a 6-degree angle. So the trig function that I'm going to use is tangent, because I have the opposite side and the adjacent side. So tangent of 6 degrees is going to be equal to h over 100. So to solve for h, I would multiply both sides by 100. So I'd have 100 tangent of 6 degrees equals the height. So the height is going to be 10.510 feet. So if the road climbs at a 6-degree angle, it's going to have a vertical change of 10.510 feet. And then to actually calculate the grade, it would be setting up a ratio. It would be 10.510 divided by 100, which is 0.10510, or 10.510%. You didn't really have to set up that secondary ratio. Just know that whatever the height is, if you divide it by 100, that'll actually be what the percentage is. So let's say the height was 8 feet, then the divided by 100 would be 8%. Take a number divided by 100, it gives you a decimal, but then to calculate the percentage, you'd have to multiply by 100 or move the decimal place twice anyway. So the idea here is you need to set up the triangle to find the height, and the height is really part of the ratio to find grade of a road. So all of these examples are right triangle examples. The idea would be kind of take the problem, take the context and draw a picture for it, and then label what you know so that you know what you're trying to find. It's a really good idea to kind of be consistent with where you label things, how you label things, so that you can keep straight what you're trying to find.